Here we go. Boom. Green numbers. Hello and welcome back to Calculus 3. So exam 1 is behind us. Exam 2 is on the horizon. And then maybe a lab or two coming up. We'll see. The topic of the day is directional derivatives and the gradient. We already talked about partial derivatives, and we know that partial derivatives are partial in respect to x or y axis, which means the surface will have derivative in that direction. And when you take the derivative at the point along any of those axes, which are partial derivative of x or y, you will get the slopes in those directions. But what if you want to go in between? So we are going to now talk about the directional derivative, which is going to fill the role of the rest. And to understand the directional derivative, I believe it's really straightforward. All I'm going to do is I'm going to take the partial derivatives and multiply that with the unit vector in a direction that I want to measure the derivative. So it's a combination of all of the vectors. Now, again, we write the definition in terms of the limit definition, but then the calculation will actually be done with a simple dot product. So it's, again, two levels. The honors section will know both formulas, even though you will not be calculating either with the limit. You just need to know the partial derivation. This one is not harder than that. It just has u's around. It's not a big deal. But still, as I said, the vanilla Calc 3 will use the dot product exclusively, either to define it or to calculate. So let's start with the definition of the directional derivative. So let f be differentiable at a, b. So f is the function of, right, x, y. Be differentiable at a, b, which is a point. And let vector u, which is u1 and u2, be a unit vector. In xy plane, so you can just say r squared. That's a terrible r. Much better. So the directional derivative of f at point AB in the direction of u is so it's a good old limit So that's the definition, but obviously that is not how we compute. What we are going to use is directional derivative in directional vector u of a, b. Now that's a u hat. Every time I write it, it's a u hat. It's a unit vector. Is going to be the partial derivatives computed at AB dotted with a vector, with a unit vector u. So that's the formula we are using. So the derivative in any direction would be the vector of partial derivatives times, I'm dotted with the direction in which you want to calculate. Now, unit vector has a magnitude of 1, so when you are multiplying by unit vector, you are fixing the direction and you are not touching the magnitude, right, of the original vector. So the u is just going to change the direction of that. So you have to be very careful to actually get the vector. So let's find a problem. So how about let's consider a function which is one of those elliptical paraboloids. You immediately think of the umbrella, right? So I give you f of x, y is 8 minus 1/2 x squared minus y squared. It's elliptical because the numbers in front of x squared and y squared are not the same, right? So it's going to be an umbrella that is a little bit squished on two sides. And we want to compute at the point, let's say 1, 1. And the unit vector u. Now you gotta always check. If someone tells you unit vector u, you check first and then use it. Root 2 over 2 and root 2 over 2. You should be able to do this immediately. You know how to find partial derivatives, and then you compute them at the point, and you know how to do dot product. So you have 18 seconds, no pressure, go. So first we verify that this is a unit vector by checking that the magnitude is 1. We can do that by doing the square root of 2 over 2 squared plus square root of 2 over 2 squared. which gives us 2 over 4 plus 2 over 4, which is 4 over 4, which is root of 1, which is 1. Awesome. So it is. Next, we need partial derivatives. Partial derivative in respect to x is negative x, and partial derivative in respect to y is negative 2y. To find the directional derivative in direction of vector u computed at point 1, 1, we are going to take the vector of partial derivatives computed at 1, 1. In this case, it's negative 1 and negative 2, and dot that with root 2 over 2 and root 2 over 2, which will further give us negative root 2 over 2 minus root 2, which is negative what? 3 halves root 2. So it's very simple to compute these things. Just be careful, be systematic. Make sure that you actually have unit vector. Sometimes on exams I troll by giving you vector u. I don't put the hat on top. I just say, here's the vector u, and I put the vector u to be 1, negative 1. Vector 1, negative 1 is not unit vector. It has magnitude of root 2. So you have to be careful. If you don't have a unit vector, you have to create the unit vector by using the formula vector u divided by its magnitude. And then you are allowed to use that vector in the formula for directional derivative. So that's one of the common mistakes. I think I saved you some of your hair, because some people are pulling the hair out doing the homework, trying to figure out why. You know, it's a simple dot product, but it's not correct. Why? Well, your vector u is not unit, so that's why. Believe it or not, that's all on directional derivatives. And now we move to the second part, which is the gradient vector. So the 2D gradient vector. Oops. So 2D gradient vector has this notation with this upside down triangle called del. That's red del. So del f xy, it's 2D, so just xy. And what it is, it's just a vector of partial derivatives. Now we already used this before. Now we're just giving it a name. We can also have component form. And now we can write the directional derivative as gradient f computed a b dotted with vector u. That's a much shorter version now, right? Because you compute first, you compute the gradient, and when you compute the gradient, right, you compute the gradient at AB. So let's pick out some of the homework exercises now. Yes. Yes, that was the definition for it. Except we wrote it out. Now we're writing it as, so yeah, this thing over here is del F computed at AB. Yeah, we're just rewriting the formula. Okay, so let's compute the gradient. Compute del F at pi, 3 pi over 2. I know how much you love trig. For fx, fxy, for fxy equals to sine 3x plus 2y. So compute del F at point pi, 3 pi over 4.
funny. That's, I guess it's like a free space. It could be a wow. Yeah, it's like one of those like bunker sweater things, isn't it? You ever see it? Oh god, they're so dumb, I hate them. Oh wait, no, it's not IE. You have like three variables. You ever seen these? Yeah. Well, it's like if you want to have that look where you're like wearing a t-shirt, God knows why. It's like if you don't want to wear a t-shirt. Yeah, Howard wears those. Howard's he's the Jewish one. But here's an instance in which I guess we were if you yeah. Oh man, but it's a look. It's a look. Oh, that's Alan. That's very unfortunate. Sorry, fella. Actually, I don't know. Who is this? Whatever this is. So I remember. Shut up, there's been several Peter Pan movies and not all of them have been animated. Shut up.
Okay, so we know that we are supposed to find the vector of partial derivatives here and then just compute at a point. You can do this in two steps if you want to, or in one. I would first find the gradient, which is partial derivatives. So when we take derivative in respect to x, derivative of sine is cosine, and then 3 floats in front. So 3 cosine 3x plus 2y. And then comma the vector for partial derivative of y, which is, in this case, 2 is going to jump out and have the cosine of 3x plus 2y. So that's the vector. The next order of business is to find the values, so pi and 3 pi over 2. So that's going to be 3 cosine of, now 3x is 3 pi plus another 3 pi, so that's 6 pi altogether. And then 2 cosine, again, same, 3 pi and plus 3 pi. So that's equal to the vector of 3 cosine 6 pi, 2 cosine 6 pi. Now that's just 3, 2. So I hope you all have this quick. The next problem is to find the directional derivative in direction of u f at point 1, 2 in a direction, the vector given as 2, 1 for the f of x, y oh sorry, this is negative 1, 2 over here. Yeah, negative 1, 2. The vector is 2, 1. And the function is ln of 4. And I should do that here. Function of xy is ln of 4 plus x squared plus y squared. Less crowded. So find the directional derivative at point -1, 2 in a direction of a vector 2, 1 for the function ln 4 plus x squared plus y squared. Yes. Yes.
If it's not a unit vector, can you do anything?
Make it a unit vector.
You can make it a unit vector.
Yeah, George paid attention, so tell him, George. There we go.
Hang on, one more time. Oh, that's right. Is that what you were laughing about?
If you like Huskies, you would understand. What's the first order of business? Find a unit vector, yes. Is the vector that it's given to us unit? Nah. So we start by creating a unit vector by taking the original vector and dividing it by its magnitude, which is 2 squared plus 1 squared is 5 squared, so root 5. So now we have that the unit vector that we have to use is 2 over root 5 comma 1 over root 5. That's the unit vector. So if the vector that it's not given to you, right, the vector is given to you is not unit, the first thing you have to do, no dancing in class, is to find the unit vector. Now you find the gradient, which is the vector of partial derivatives. So ln, so we copy the function and then the derivative up would be 2x, and then symmetry, right? And now we compute this vector at -1, 2. So we'll get -2 divided by 4, 5 plus 9. And then 4 over, again, 9. And then directional derivative in direction of u of f, which is computed at -1, 2, is going to be -2 over 9, comma 4 over 9, dotted with the vector 2 root 5, 1 root 5, which gives us the vector -4, 9 root 5, and 4, 9 root 5. Now you can rationalize this to make it better, which would give us -4 root 5 divided by...
It's a dot product.
The hell did I do? Oh, I'm supposed to add them. The hell am I doing? It's a dot product. Plus, and we get... There we go. Wonk, wonk. Okay. Yeah, I was just testing if you guys are paying attention, and you do, so that's great. Very good. Now let's see some of the applications or interpretations of this. And you will definitely see these types of problems on your homework and possibly on the exam, which is what is this used for, these directional derivatives? So we know that derivative measures the rate of change, right? And we know from Calculus 1, if we have some kind of a function, the steeper, right, over here the tangent line looks like this, over here tangent line looks like that. So the steeper it is, the steeper the tangent line. So if the function rises quicker, steeper the tangent line. So now directional derivatives do the same, except they do that for the surface. So you want to picture yourself on a hill. If you go outside, right? Let's say you go outside. There's this thing called hiking. Not hitchhiking, hiking. And you are on the side of the hill, right? The higher the slope, right, the harder it is to walk. So that's what the directional derivatives, at the point, the highest, the largest ascent and the largest descent will happen in the direction of the gradient at that point. So the steepest way up and the steepest way down is always in the direction of the gradient at any given point. And if the gradient is 0, then the direction is perpendicular to the surface, because the dot product is 0, right? We just had the example of that. So imagine some kind of surface, and you are walking on the side uphill. So at any point where you stop, if you compute the gradient, obviously this hill surface will have equation, and then at any point along wherever you stop, the greatest slope up or down is given by the gradient. So that is captured in this theorem 1211, which says directions of change, and it says f has maximum rate of increase in a direction of the gradient, and then f has its maximum rate of decrease in the direction of the negative gradient. So let's write those down. Number one, fxy has its max rate of increase at point AB, so that's where you stand, in the direction of the gradient del FAB. So you know that that gives you a vector. Let me just go and find the example. You guys see that we computed over here the gradient at point AB, and we got 3, 2. That's a vector that points in certain direction in space, right? And the rate of change in the direction is given by the magnitude of that vector. And now you copy the same text except minimum and it's negative. So function fxy has its minimum rate, sorry, has its maximum rate of decrease. Maximum rate of decrease. At point AB and the direction of the gradient, which is negative now. Again, the rate of change. So that's the slope, right? In this direction is the is given by negative absolute value del FAB. And finally, 3, the directional derivative is 0. In any direction orthogonal to del FAB. And that was the previous example when we got 0. So now you can compute the steepest ascent and descent. at any point on the side of the hill or whatever you have equation for. So here's the example for that. So what do you have? Direction of steepest ascent and descent. Find the unit vector that gives the direction of steepest ascent and descent. Find the vector that points in a direction of no change. So technically do all three. What are the specs? Let's see. What is that thing you like? Oh, here. F of xy is given to you by e raised to the negative x squared over 2 minus y squared over 2 for the point negative 1, 1. So you are looking for direction. So find the direction of steepest ascent and descent.
Squared, but at negative negative 1 half minus
Okay, let's see. So we know we are supposed to find the gradient and then compute the gradient. Positive goes ascent, the negative is descent. So del f of xy is, and now we take the derivative. So this is e, so it stays as is, and then times the derivative, right? So it's just going to be negative 2x, right? Oh yeah, over 2, so negative x. So we have negative x e to the negative x squared over 2 minus y squared over 2, and then negative y e negative x squared over 2 minus y squared over 2. So now we compute del at negative 1, 1, and that's going to give us the steepest descent immediately, the direction. So plug in negative 1, we are going to get 1, so we don't have to write that 1, just e to the, is that negative 1? And then we also have negative y, which is now going to be negative e to the negative 1. So to write it nicely, 1 over e, comma, negative 1 over e. So that's the direction of the steepest ascent. And then we have negative del f negative 1, 1, which has to be the same thing, just the opposite direction, so minus 1 over e. 1 over e, steepest descent. Okay, one more quick theorem. So, given a function f is differentiable at AB. So this theorem is going to connect level curves and the gradients. And the line tangent to the level curve of f at B just notice that this is not that happy, so I'll just write at. So given a function f is differentiable at AB, and the line tangent to be the level curve at AB is orthogonal to the gradient. provided it's not 0. If you have a level curve, you are going to have your tangential vector and your gradient vector. And they are perpendicular, which means 90 degrees. All it's left is just to bring this one dimension higher. We don't have to do any problems or anything like that. I'm just going to define the gradient now in 3D. So del f of x, y, z is vector of partial derivatives. You can also put the I, j, k components if you want to. And then obviously it works for the dot product again on a 3D surface, dot product with the unit vector to give us the directional derivative in 3D. And then we also have the steepest ascent and ascent and everything else. So the whole thing moves. I'm actually going to write the short formula because I can. That's the short formula again. And that's 12.6. I hope you're not disappointed. You will have 3D cases on the homework as well. It's the same as 2D case, except you have one more, right? Partial derivative to take, and you have one more dot product, right? Multiplication to do. That's not new concept. All right, so that's it. Let's say bye to the stream. Bye.